Okay. So we just had a pretty good discussion. Allowing people to share what they did in lab last time. That's then and let other people explain what had been explained to them. That came out pretty good. Then ask everybody to prepare a good quantitative analysis of their experiment. Share with everybody in lab on Friday. Okay, so I want to go ahead and start reviewing. Nobody had a better idea, any consensus on something better to do. Just because it's my idea doesn't mean it's the best. Okay, so I'm going to review. Okay, first of all, I'm going to review the most recent stuff first. The stuff that we've done since midterm, pretty much stuff on electricity and magnetism. Okay. So what I really think might be the best thing to help tie things together is to review the premises behind everything you've done. Okay. Because if you have a good grasp of the premises, it makes it easier to remember the details. Okay, so first of all, I'll just we have Coulomb's law, right? And we have Gauss's law. Both of these relate to electric fields. These are fundamental. Then we have Ampere's law. Okay. I don't care if you don't remember the names. I don't focus much on the names. These ones come up. Ampere's law basically says you integrate around the loop. Okay. And integrate the magnetic field around the loop to get to EMF. Okay. So really little comments, but it's kind of going to be what we want to see. And then Faraday's law. Says up here, EMF is equal to the rate of change of magnetic flux, something you've seen quite a bit of. Okay, I'll start with these. Yeah, it's not the worst. Okay. Coulomb's law gives you the rule for the electric field. Well, it gives you the rule for the force between two conductors, between two charges. Okay. So let's start with that out. Equals K Q1 Q2 over R 1,2 squared times your R 1,2. Okay. And your picture goes with that if you got Q1. Q2. There's your R12 vector. And R12 half. Meaning a unit vector with the rest of the R1. You've got R12. Then you've got R12 half. And then you have the force. If the two charges are both positive, this is going to be a positive product. Bigger force is gonna be in that direction, force exerted by T1 on T2 is in that direction. If T1 and T2 are opposite charge. It's gonna be force of attraction in the direction opposite to normal. That's very simple, that's the basis. Then, your electric field. Is A cubed over R squared times. In R hat, and this means you have charge capital Q to it. And you got a point. X, Y, Z here. Here's your R there. And here's your unit vector R hat, which is just, of course, R divided by studying it to everybody's very familiar with that. And that gives you an electric field. So typically, if you're forces with the clip of which if you force a good connection. It's not really along a straight line either. I have no idea how to fix it. Okay. Now your electric field due to a collection of charges. It's just the sum of your K Q sub I over R sub I squared. Or hat sub I, I'm not going to draw a picture, but you have 3 or 4 charges, you draw the same picture. Draw this picture for each charge, and you add up your field. Actually, it's 2 charges, so we got like a Q1 here, and Q2 here, and we want the field at a point. And let's say the point is, and let's put it. And let's put it here. Okay, so we got our 2R vectors. This will be your R1. This will be your R2. And that's how you see it. Okay. I'd be hard to read my subscript. You should know what I'm doing. And then depending on which of these is bigger and combination of bigger and closer makes the field vector bigger or smaller. I'll assume here's our E1. Here's our E2. And our E is just going to be what we get from the parallelogram, or from adding the vectors head and tail. And you should totally understand that addition. In other words, if I do E1 head to tail, E2 starting with E1. And here's E1, here's E2. And here's the results. Okay. So you have that picture in your head, if you got finite, a small finite number of points, up to maybe 4 or 5 points, you should be able to make a sketch. And kind of see how that works. And maybe at several different points, there's some kind of configuration. You got 4 charges at the corners of a square. Maybe they're different charges. Okay, maybe you draw a field. Couple of points out here and out here. Maybe from the other side, depending on what symmetries you have. Okay, so I can't really describe that or draw a whole lot of pictures in the time they have that. But then we draw pictures. Okay. Now, another expression for E total. Integral. In general, would be an integral of the volume. Sometimes it's over there, sometimes it's over a line. And you just integrate. Okay, times the density, it might be a rho or sigma or lambda, depending whether it's a line charge, a plane charge, or a charge distributed over a volume. And I won't say D X or DA or D B could be again over volume. Surface. A line. You can get that. And those are basic principles. Now you get into the application. Well, if I give you 3 or 4 charges and ask you to calculate the electric field at a point, it should be very straightforward. Okay. You should be able to. If I give you a charge distribution, you ought to be able to set up and the region is available to setting up coherent integral. You have one. Okay. I will mention. And just go you picture, you know, line chart. And then you partition. You know, because that's when we have a parameterized partition. And you maybe want the electric field at this point. And maybe you draw a few selected dotted lines indicating the direction of electric. Probably don't want to try to put those in all of those records. Overlap each other and stuff. But you should see that if this is a uniform line charge, you're going to get a pretty small field from this point. But then symmetrically over here, you get this. And then from this point, which is quite a bit closer, you know, it's exactly like this, exactly like this. And you got this like bubble of vectors that are symmetric around a line through the point perpendicular to the chart. Okay. I usually don't be able to set that up for you. You can have that picture so you understand how things work. Because to go a little further, you have the electric field loop. Center loop is real easy. Not going to do, but at some point up here, you get something very similar. From diametrically opposite increments. You get field contributions, for which the component parallel to the plane of the loop or perpendicular to the axis. Those components cancel each other out, and you just end up with components in this direction, and they all add up. And I especially mention that because that's how you're going to calculate the magnetic field due to the current in the loop. And of course, in a loop, then what you have here is your I ds. Okay. Okay. And you really kind of want to know how this relates to this field at the center. No, just comment, it's just this vector is longer by a factor and involves the Pythagorean theorem. And what happens with complements, we kind of reason it out quickly if you know the relationship to the center, which is straightforward and not going to talk about. Okay. Or you can go to the total set, not the whole equation. Make sure you got your vector components on. Okay. Okay, so we don't have time to go into all the detail of this. Perhaps if there are specific things you really want to see again, we have time to do that on Thursday. But we'll see. Okay, well, that's a whole lot about electric fields. And then, of course, Gauss's law. Flux being electric field is 4 pi. Okay. You enclose. So that if you have a sphere with a charge distribution that's symmetric with respect to the center of the sphere, you know you have the same electric field at every magnitude of the electric field is the same at every point on the sphere. Field is always perpendicular. So for a sphere, this comes out just 4 pi squared times the radius. Maybe surface area times the electric field. Get this. 4 pi a squared times electric field. So then if you divide this out, you get your electric fields KQ over A squared. Okay. For a minute, I was looking at that. So the brain freeze that. Okay. I just wanted to get a full fine result or something. Okay, well, that's for a sphere. With the appropriate center. Okay. And then we can do the same thing for cylinder, and you get 2 phi a L. And we've done this with reminding you. Times E. And then for plane distribution of that picture. We've got a plug through the distribution of any shape of the cross sectional area. A. Then you get um, you got the flux from the left and from the right. That'll be the cross-sectional area times 2A times the cross-sectional area times E equals 4 pi K. Your Q enclosed. Is 4 pi K times sigma times your cross-sectional area. So when you solve with the electric field, you get 2 pi K sigma everywhere. Now the area, cross-sectional area, of course, divides out because you got to multiply the cross-sectional area by the uniform charge density. So, and that's a start on Gauss's law. And then you have things about concentric cylinders and all that stuff. Once you understand it for a line, well, first, a distribution symmetric about straight line axis. Okay, then everything pretty much falls out. You just got to do the problems to get used to it. Now there's some subtle things. Yeah. So you might review some things you have seen. In the put aside hope. And also in the text. Okay. Something I'll add here is I was going to make that a field source. About love violence apart. I don't know how you pronounce his name. But it's a picture. Okay. So we probably actually want to start with a source of a magnetic field. Charge Q, moving at velocity V, electric field, out here. Okay. And it's in a lot of ways analogous to Coulomb's law. It's K prime times QV. Cross on over R squared. This will be times an R hat. Unit difference. So because of the cross product, this thing depends not only on the distance, but on the sine of the angle. So the further the angle is from 90 degrees, the less the magnetic field is going to be. Okay. And you got to work that out. The other picture. If you've got the current I going along the line. You got a point here where you want the magnetic field. total magnetic field. You take, well, you partition this one. So this might be an infinite charge distribution or an essentially infinite charge distribution. Because you get too far out along here and your distance is going to be squared and the sine of that angle are both pushing this thing towards zero. Okay, and you should do the integrals. You should look at the difference. You should look at the integral from, let's say, 10 times this distance this way. So you ignore everything within 10 times that distance and do the integral for that. What's left in that direction and what's left in that direction is going to be a whole lot like what's left in that direction. Okay? You see the difference between what you get for finite and an infinite charge. Okay. In other words, see how much you lose there and how much you have then on that second section. Okay. You know, even compare what you have within just this distance. You got most of it. Figure out the point at which you get most of it. You probably don't have time to do all that, but you want to think about that. You want to think about how you'd set it up. Just so you understand that it doesn't take very long to set it up. You don't want to probably have the time to do the integral. You go to a machine and do the integral. Okay. Just to get the idea. Now you should look at the integral and think here's a technique I'm going to use. Here's what's going to happen. Because it gives you a much better feeling. Okay, we'll take that for what it's worth. You think of partitioning, whatever interval. And you know, this could be a finite interval because very easily you could have a current running from the source down here. Like that, and like this, it runs in this direction, right? You're not going to get much contribution to the field here from this, or this. Phones are much closer to this than they are to the end. So these, intervals over finite distances become important. Well, anyway. So whether it's an infinite or finite distance, whether it's set up like this or somehow, you're just treating it as though it's infinite. You take a typical negative, get your R vector, get your ideal, let's say I delta S, okay? And the delta S we have vector quantity, and you calculate what's the phase quantity. And if you think in terms of mu naught, just remember K prime is 1 over 4 pi mu naught. Mu naught 1 over 4 pi. Okay. And I said that wrong, 4 pi, but you know, 1 over 4 pi. All right. So you want to, again, understand your source of the magnetic field. Now, if you got the magnetic field due to a loop, you do the same thing. It looks like this. Get the field along the axis, which is totally relevant to almost everything we were measuring in lab last time, right? So if you haven't derived this expression for an arbitrary distance along an axis, probably ought to, because probably going to see it. You have a high probability of seeing it on the exam. Among other things, it also you need that to really make sense of what you've been looking at. And then you can compare the results you get from the integral you do here for magnetic field. Um, If you kind of bring yourself to a full circle understanding what's going on. Okay, now, if you do this thing for, okay. If this is the end, look at end on, that's a charge carrier. You see with the magnetic field. It's coming out of where magnetic field lines loop in separate circles. Okay, meaning the magnetic field at any point is tangent. This one, what's my magnetic field here? Magnetic field here. Magnetic field here, here. Bigger magnetic fields here. Here, and everyone here. Your infinite wire falls off and R. So if your voice is understand twice in the field. And you didn't know how to work that out. That's pretty much the basis for what you need to know about the magnetic field source. It's either moving charges, or for most of what we've done, drifting charges. Current, it's either a straight line or a loop. Other current configurations are much more difficult. They're great, and a lot of times you got to use approximations, look things up, look up what somebody else measured. Ampere's law relates. You get when you integrate the fuel around the loop. Right. And think about that for a minute. I was almost ready to hit it again. Okay, so anyway, if you were to calculate the current due to, the magnetic field at a point due to current, and do that along a concentric circle, then it's really easy to verify that the integral over any one of these paths I dot ds is equal to what? It's equal to a multiple of I. And I'm gonna have to work out what the factor is. Okay, simple enough. The distance r, where everything's perpendicular, for distance a, whatever, you're going to get 8 prime times I over a. So along one. Um, if you multiply that by the circumference, you're gonna go by ds, because your current is always perpendicular to that loop as long as it's centered at the axis of the current. Well, I'm getting. I'm really gonna lose the factor here. I don't think that's what I get when I reason that out. Is just on. K prime I. Now that 2 is bothering me a little bit. I'm doing this off the top of my head. I'm going to check some. Okay, as I think it actually be a 4, just something wrong with my little calculation. It's like I should be getting a 2 up here. I don't see it, but set up to anything to do it. So anyhow, you got this. This is for the current and long wire. Now, the one thing that should stick with you is when you integrate the reciprocal R squared, you're going to get a reciprocal R. It's going to be reciprocal A here where A is the distance. And field, as I said earlier, falls off proportionally to the distance from the source. Okay. And the circumference of this loop is proportional to the distance from the source, so that the distance from the source isn't going to matter. Now that's really kind of a key thing you want to understand. You want to understand that proportionality. It just helps you think about what's going on. Then if you remember, or if you can think clearly enough, see what the 2 is, you get a 4 pi k instead of 2 pi k, or a mu naught x k prime. Okay, or mu naught. U naught times I. So Ampere's law. You'll be able to easily look through the details here and verify it in this situation. But in general, and magnetic field, not the current and source. This is the magnetic field. This is not the current. We're integrating around here is a magnetic field. Magnetic field is apparently 2 k prime I over A. And how we get this? This applies to anything. So, for example, the example of a solenoid, which is relevant to one of the devices, one of the puzzle wire that you will use in the lab. You've got a cylindrical core, a bunch of wire around it. And you use a panel. looks like this. And you integrate around the path. So here's your path C. Reasons that we talked about, symmetry, distance, and so forth. You have essentially a zero contribution of the integral along this path and this path, because they're going opposite directions, experiencing the same field through the symmetry, as long as they're not too close to the edges. Okay, this is far enough away, it could be as far away as we like, far enough away that it makes a negligible contribution. So the whole integral is along there. Okay. So if we did this in detail, you can always review it. But the equal to the current times without notation in your book is always a little bit confusing. They use an N, the number of loops per unit length, when N seems to connote the actual number. So I don't like that notation. So I'm going to even just write it out. It's going to be I times number of loops that you can close here. However, that's, you know, times, I'll say delta x, for delta x is whatever length of the coil you happen to be in. So to get the number of loops, you take the number of loops per unit length, and the total number of loops divided by the total length, which is the number of loops per unit length. And you multiply that. Well, you multiply the number of loops per unit length by your delta x to get the number of loops. Okay, but your ds is then your delta x. I don't want to confuse that with the delta phi. B is by symmetry parallel to the axis. So your B dot ds is just a simple product. And everything works out. Okay. So you want to understand that argument. And for circular loop, you're going to use, and I ask you to read that, I'm not going to say it even now. You need to pull that out and get to the next. But the idea is simple. If it's a circular solenoid wrapped around a donut, you just use a path, circular path within the solenoid. It never has to go outside the solenoid. So you can easily figure out how many loops you can close or so forth. Okay, you can close them all. Okay, it's actually simpler than this. They're both pretty simple. So you want to understand both of them. And then how to use the whole idea. Well, got a solenoid. I estimate you've got 20 loops per second. Okay. So that would be 2,000 loops per minute. Length of the thing is about 5 centimeters. Okay. That's all the information you need to figure out what the magnetic field would be here as a multiple of the current. Okay. So very straightforward for the wire loops that you can use. Now you can figure out things about the conductor in our circuit board here. Got a pretty high inductance. Using pretty small wire, lots of turns and whatever, I don't know what the core is. Well, core is empty. You put a wire in it and look at what happens. You double and triple the magnetic field and we absorb it. I don't know if there's anything between the loops and the center. It also enhances the magnetic field because it's got a, almost a 100th of a Henry. That's a lot of inductance. Really need to look into how these things are built and designed. Okay. Okay, well, that's Ampere's law. It's one of the things that's good for it. There's a lot more by doing the problems. Right. And by getting your hands on it and thinking about what you've got your hands on. Faraday's law. Induce the EMF, change the magnetic flux through surface. Okay, if you've got a loop of wire or the Helmholtz coils, whatever, well, you measured that. Everybody's seen that, experience it. Okay. Hopefully you believe it. Now from this, we could then very easily calculate the inductance of this form. Incidentally, once you've got this integral of V dot ds, well, you know what the magnetic field is inside the coil. And one of the big things about the coil is self-inductance or solenoid or loop. Okay. If you change the current, you change the flux, magnetic flux through that coil itself. And also through any other coil loop that the thing happens to be oriented to. Okay. Take a lot of words to say what I really tried to say. You get the idea because that's one of the things we talked about at the very beginning of the class in terms of what we did on the lab. So that's I think we did that. Okay. And the EMF opposes the change in magnetic field. That negative sign there is there because of the opposition and of other things. Okay. We can go on with this, but we have a limited amount of time left. Also, the IDC equals how you do for voltage. Leading into equations of LDI dt. That's all right. Around a loop, okay, voltage, or even to we have a capacitor, got a voltage drop Q over C. Of course, this equation has two variable quantities, Q and I, but fortunately they're related because I is just dQ dt. giving us this equation, which is a familiar differential equation. Again, you're not gonna be testing, hoping your ability to solve a differential equation, or maybe be able to verify a solution. And if your skills, you want to use your skills from differential equations, you're welcome to do it, because it comes through a lot of stuff. One big thing to see out of this, two last thing we talked about, is that, if you have a side soil, correct, that, you have a phase relationship between these things. The other one side is out of phase with the sun by 90 degrees, and remember that is out of phase by 90 degrees. This is 90 degrees from this, this is 90 degrees from this, and opposite directions gives you phase. Using magazine, stuff like that. We'll talk about that in a second. And of course, you have voted cross reserve. Some proportion. You're correct. Okay,